that's going on in the energy field. Our first presenter will be Casey from the Missouri University of Science and Technology, and then uh, Sarvanaz from the University of Missouri, Kansas City. Michael will join us from the Electric Power Research Institute, and Jennifer will close us out, and she is from the National Renewable Energy Laboratory. So hopefully we have a lot of positive things to look forward to coming out of this presentation. Remember, ask your questions anytime during the question and answer button on your screen, and we'll make sure that we get those addressed. So with that said, Casey, if you will hop on and join us, we'll love to hear what you have to say. Welcome.
Awesome. Thanks, Josh. Okay,
absolutely. You're perfect. Okay, awesome. You're ready to go.
Awesome. Okay. So, hey, I'm Casey Canfield, and I'm an assistant professor in engineering management and systems engineering at Missouri S&T down in Rolla. I joined the faculty in 2018 and was previously a science technology policy fellow at the Solar Energy Technologies Office in the U.S. Department of Energy. And my PhD is actually in engineering and public policy. So in my presentation, you'll see that there's a policy angle for most of my research. Next slide. So first, I wanted to give an overview of Missouri S&T. So Missouri S&T is a pretty small institution with almost 8,000 students, but there's a lot going on. We've got basically every engineering degree you can imagine with 99 degree programs, and there's a big emphasis on hands-on project-based learning. If you've been paying attention to the news, you might have heard that S&T recently received a $300 million gift, which is being used to stand up the Cummer Institute. This gift is expected to dramatically increase the research capabilities of the institution and foster more commercialization and entrepreneurship to boost the local economy. There's a long-term plan to build a research park at S&T in the tradition of something like the Johns Hopkins Applied Physics Laboratory or a national lab or something like that. So definitely keep an eye out for developments. Today, I'm going to highlight 3 of my projects related to energy, and then I'll highlight 3 other research efforts that are going on currently at S&T. Next slide. So I'm currently in the process of wrapping up an evaluation of the impact of the SolSmart program. SolSmart is a national designation program where local communities can get a gold, silver, or bronze medal for completing best practice actions that streamline requirements for solar installations. And these actions range from posting information on a website for how to get a solar permit to having a 3-day turnaround for solar permits. In Missouri, there's actually about 10 SolSmart communities, including Columbia, and a bunch of communities in and around the Kansas City area. In this evaluation funded by the Solar Foundation, I worked with other researchers at Florida State University, the University of Texas at Austin, and the University of Miami to determine whether this type of voluntary program has any tangible impacts. So we gathered data from the SolSmart program, as well as several other external databases, to measure the impact of SolSmart using quasi-experimental methods. So to do this, we first had to really carefully match SolSmart communities with other communities that did not participate in SolSmart, but were otherwise very similar communities. This helped us estimate what would have happened if the SolSmart communities had not participated in SolSmart. So in the diagram, you see the dotted orange line. That's basically our counterfactual. So if the SolSmart communities, represented by the orange line, had not participated, they would have followed along the same parallel trend as the non-SolSmart communities, represented by the blue line. And so by looking at the difference in terms of before and after SolSmart, we can say how much change was specifically because of SolSmart versus just the fact that the solar market's maturing in general. And so we found that SolSmart increased the number of installations by 3 systems per month. And we estimate that the national impact was an additional 12 to 19,000 installations because of SolSmart. There was also higher installed capacity and faster permitting times in communities with SolSmart. So from a financial perspective, the US Department of Energy invested $10 million into the SolSmart program, and there was an additional $1 to $2 billion investment in the solar market. So this suggests that a voluntary program like SolSmart is really effective for boosting the local solar market. So we should look at getting other communities in Missouri to participate in this program. Now move on to the next project. So I've got another project looking at principles for designing electric rates in the context of prosumers and distributed energy resources. So I'm working with an economist at S&T named Mahalet Fikru, and we're deriving equations to construct a framework for comparing different approaches for rate design. When we think about the future of rate design, there's a lot of different factors that we can focus on. So rates can vary over time, like time of use rates. We could have different rates for specific technologies like solar and electric vehicles and batteries. We could have equity-based rates that rethink approaches like LIHEAP for low-income assistance. We could have real-time dynamic rates to give consumers the real price signal from the market. So far, we've published one paper introducing this idea and applying it to location varying rates. So we start with location varying rates, mostly because the math is simpler, but also because this might be an effective approach for simplifying dynamic rates that vary across time and location to be more understandable to consumers, because they only vary across location. And so for the location varying rate, we're deriving a rate based on the marginal principle. So each household is paying for how much it costs to deliver 1 more kilowatt hour of electricity to that household specifically. And so the picture on the left outlines the basic framework that accounts for demand and various utility costs. So we assume that customers vary in terms of demand, ownership of distributed energy resources like solar, how much electricity they inject into the grid. We also account for utility system costs, such as fuel costs, the cost of distributing electricity, ramping, integration costs, congestion costs, and net metering compensation. And then on the right is a figure from some additional work where we're running a Monte Carlo simulation in order to understand how sensitive the comparison between a traditional uniform rate and a location varying rate is to the underlying assumptions. So the x-axis here represents the percent of demand offset by solar. So if you're at 0%, you're a traditional consumer. And if you're at 100%, you're completely off grid. The y-axis is the electricity rate. And so this plot shows that the utility system characteristics drive a lot more of the uncertainty in the comparison. So under a uniform rate, everyone experiences that uncertainty equally, as you can see from the shaded green part. And then with a location varying rate, shown with the blue line and the pink shading, the consumers are increasingly insulated from any uncertainty associated with the utility system. As you can see, it kind of narrows down as you get towards 100%. And so we've got plans for future work that further explores other principles that vary based on time and technology and other factors. There's also a lot more to explore here in terms of equity impacts and cross subsidies, utility business models, and consumer behavior responses to price signals. And then I'll go to the next project. And so the last project of mine that I'll mention focuses on renewable energy procurement. So very relevant for the last series of talks. So in order to address climate change, we need more people to adopt renewable energy. The good thing is that demand for renewable energy is increasing, so there's more options in the market. You can put solar on your house, or you can sign up to pay a little extra for your utility to provide all of your electricity from renewable sources, like, for example, the solar farm here on the left. And so in a project funded by the Sloan Foundation, we're studying whether having more options changes people's interest in installing solar on their homes. Specifically, we're looking at whether having all these like virtual options, and I'm using the word virtual a little differently than in the last set of talks. So thinking of virtual options as community solar, green utility pricing, green tariffs, just having those options available make people more or less likely to choose a physical option like installing solar on their roof. We're also specifically looking at community choice aggregation, or CCAs, which rely on an opt-out structure to allow a community to negotiate for more renewables and lower prices for electricity. And so for this study, Dr. Fikru from the economics department and I are partnering with a CCA in California, the Silicon Valley Clean Energy, and a CCA in Massachusetts, Cape Light Compact, as well as the National Renewable Energy Lab. And so to answer this question, we'll actually be spending the next 2 years analyzing market data from our CCA partners as well as NREL, and distributing experimental surveys to collect data on people's preferences. So this will allow us to understand how people are behaving right now, as well as make predictions on how people might behave in the future if we can figure out new ways to market and package renewable energy procurement options. And so this has implications for utility business models and planning. So for example, if people treat them as substitutes, these virtual and physical options, then there will be increased demand for utility scale renewables versus distributed renewables. But if people treat these virtual and physical options as complements, then these virtual options might be the gateway drug to installing solar on your roof. So next slide. So now I'm going to switch gears a little bit to highlight some work that other folks are doing. So S&T has a Center for Research in Energy and Environment that brings together all of the folks doing related research. So this center also manages 2 living laboratories called the Solar Village, which has 4 interconnected houses, and the Eco Village, which has 2 separate houses. The houses were all designed and built by student design teams for the Department of Energy's Solar Decathlon. After the competitions, university researchers connected the houses into microgrids to explore a variety of technologies and their impact on daily life. So the Solar Village has 4 older houses connected to a centralized control system with energy storage. And the Eco Village has 2 newer houses, each with its own energy storage system. The Eco Village batteries are advanced lead acid, which we believe is a viable technology for this stationary application. More importantly, we have students actually living there in these houses and interacting with the smart appliances and other technologies. So we have active projects examining the human technology interaction and associated ethics and privacy, in addition to projects on energy management and other core engineering problems. And so if you're ever in Rolla, I highly recommend reaching out and getting a tour of these facilities. They're very, very cool. Next slide. And so Jonathan Kimball in the Electrical and Computer Engineering Department is leading a Department of Energy funded project to develop an extreme fast charging station. So the goal is to be able to charge an electric vehicle just like refilling a gasoline vehicle. This is thought to be a critical part of removing barriers to adoption for EVs. It will be connected to a medium voltage distribution network to eliminate the 60 Hertz distribution transformer. We have researchers investigating the best way to charge batteries this quickly to minimize damage, designing medium voltage power converters, and developing control methods that will mitigate the effect of this load. The power level is relatively high, and the edges can be sharp as vehicles are plugged in and unplugged. We will have a stationary battery to buffer the power demand, and we'll also have the ability to inject or absorb reactive power to regulate voltage. And next slide. So the last project that I'll highlight is led by Ray Bowe, who's also in the Electrical and Computer Engineering Department. The idea here is that wholesale electricity markets are increasingly complex in terms of spatial and temporal sophistication, which makes market monitoring difficult. As a result, profitable gaming activities go unnoticed or get revealed several years after they occur. So we need a proactive and preventative mechanism. So Dr. Bowe is working to use big data analytics and computational intelligence tools to do that market monitoring by building a market simulator to support experimental research. So far, they've focused on identifying gaming strategies and are using the simulator to determine how different market rules can actually stop gaming from happening. So with that, I look forward to the Q&A discussion at the end. Thanks.
Thank you so much, Casey. Next up is Sarvanaz from University of Missouri, Kansas City.
All right, thank you so much, Josh. So hi everyone, I'm Sarvanaz Sarbandi. Assistant Professor of Mechanical Engineering from the RT Lab, University of Missouri, Kansas City. Today, I'm going to talk about the solar energy, a widely available source of energy to give us the opportunity to make the world sustainable. Next slide, please. All right, so I'm just going to go over like one of the main projects that is already going on in our lab, which has the different components of the experimental, numerical, and computational fluid dynamics modeling and focusing on the solar water heater technology. Next slide. So let's take a look at the Missouri solar market insight. First of all, as the few presenter at the back also mentioned it. So the the total solar power installed in Missouri is 278 megawatt power at this point, with the around 30,000 of the state homes powered by the solar. However, if you take a look at the chart, you will see that there is a fluctuation in the recent years. And then we do have the projection of getting to the 485 megawatt power in the next 5 years, getting us the more benefit to utilize this free source of the energy. Next slide. So as I mentioned, the focus of my current research is the solar water heater technology. So let's take a look at to see basically how this system works. The main component of a solar water heater system is a solar collector, which absorbs the radiation from the sun and transfer it to the heat passing, to the water passing through. These type of collectors can be different, various type of collectors, such as the flat panels that you may notice that one more often in houses, as well as evacuated tube solar collectors, compound parabolic, and so on. However, the mechanism of all these types of collectors are same. They absorb the sun radiation, transfer it to the water passing through, and this hot water needs to be stored in a storage tank. So later out the day that you would like to do the household activities such as taking shower or anything else, you will have the hot water and with the temperature that is requested. However, the temperature inside this storage tank eventually loses the heat. Therefore, at nighttime, if you would like to take the shower, the water is not at the demand temperature. Therefore, there is a need for a booster unit to heat up the water again. This booster unit can work with the gas or electricity. Therefore, it added some cost to your total bill. So next slide. Our target point is basically eliminating the need for a booster system. If you take a look at the left figure, it shows the daily residential water heater demand in summer and winter time. There are actually two peak zones during the morning time and evening time, around 5 a.m. till 11 a.m. and around like 5 p.m. till 11 p.m. that consider the peak zones. Meeting the demand of the morning peak zone, it's mostly easy because of the radiation is available. However, when there is no sun, meeting the demand of the evening peak zone, that would be challenging. Therefore, the goal of this project is utilizing some source of energy, which is called latent heat storage material, or basically phase change material, to be able to use as a backup source. So how these types of materials work? These materials are inside of a rigid, tiny shell. When they started heating up, the material inside this shell starts melting. When they are melting, they are absorbing this energy to later on, when they are going to the crystallization and cooling down process, they can release this heat back to the system, but basically they can be utilized as a backup source to our unit. So this rigid shell, it just make it in a way that this melting crystallization process will not be visible, as well as it will reduce the amount of leakage. Therefore, you won't have any issue utilizing them in your system. Next slide. So as I mentioned, the main component of those solar water heater technologies are the solar collectors. Among all of those type of collectors, the focus of this research is utilizing evacuated tube solar collector because of unique specification. So first of all, ETCs are two concentric tubes which are infused at the bottom with having a vacuum between these two tubes. The usage of this vacuum eliminates the amount of heat loss, therefore we can preserve the amount of energy for a longer period of time. There is a heat pipe inside of this collector which has a small droplet of water or glycol, which basically when it heats up from the sun, that evaporates, go to the top of the heat pipe where the water passing through. Also, because of the circular shape of these collectors, it also gives us the opportunity to passive tracking of the sunlight, therefore again increase the efficiency of the system. If you take a look at the usage of these types of collectors around the world, we will see that there is a market, very great, basically potential market to growth in United States. The amount of ETC usage utilization in solar water heater technologies in the United States is only currently 1.2%. However, if you compare it to around the world or European country, you will see that there will be a great chance that we can utilize this in our technologies. Next slide. In the preliminary experimental analysis that we made, we tried to integrate those types of energy storage material inside the collector to see if they actually work. So, I mean, the previous researchers, they were utilizing this energy storage in the storage tank when the water was preserving. However, the novelty of this project was literally integrating those material inside the collector to have a direct energy release. So whenever we are targeting to modify some types of systems, the important factor is the cost. So we needed to make sure the type of material we are using is cheap, inexpensive, basically, and widely available. Therefore, we targeted two types of PCM, which the first one is a sugar alcohol, namely erythritol, which is the sweetener that basically you add into your coffee every day. The second type of PCM that we use is the paraffin wax, which is the material for the candle. So both of them are inexpensive, non-toxic, and widely available. We fill these type of materials inside the aluminum baggies in order to prevent them from sudden expansion that they can break the tube, basically, as well as we add silicone oil around these baggies in order to maximize the heat transfer inside the tube and uniform heat transfer inside the tubes. We captured the solar radiation data throughout the day by the pyranometer. And first of all, I just need to mention this analysis was done in Texas, Dallas, Texas. So it has a little bit higher sun radiation throughout the year compared to Kansas City. However, these two systems, one of these systems were untouched, so basically commercially available ETCs, and the other one was the modified version by us. And then the results show that the system with the PCM integrated in could increase the efficiency by 26%, which is a great number. And it can basically reduce the utility costs that you will need to basically heat up your water again. Next slide. So all of these trial and errors experimentally are costly and they are time consuming. Therefore, having a valid computational fluid dynamics modeling that we can predict the performance of the system as well as try to optimize and remodify the system will be so beneficial. And that's the second research project that is going in my lab. Next slide. So the benefits of the CFD is details, giving us the detailed insight of the thermal behavior of these collectors, as well as we can predict the melting fraction of the PCM. So when we integrate the tubes with the PCM, there's no way you can literally see inside to figure out if these materials, how these materials get melted and crystallized, and how you can reconfigure it in a way that you can absorb more energy inside. So the novelty of this work is just giving us the thermal behavior of the collectors throughout 24 hours of operation, which is basically the previous researchers were just ran for 7 or 8 hours operation. That's a perfect thing, as well as it will give you a better insight inside the collectors. We use the commercially available software ANSYS Fluent. Initially, they started off with the 19.2 version. Recently, we just upgraded to 2020 R2. We simulated one single evacuated tube, which has the PCM integrated inside. We needed to do like mesh independency stuff to actually get the resolution that gives us the better and optimal results. Next slide. So by applying the boundary conditions similar to the experimental, so basically we get the weather data condition, solar radiation, thermophysical properties of material, physical configuration of the system, we run the similar case to the experimental, and the actual CFD results show around 2% average deviation with the result, which is a great agreement with the experimental work, and it shows that this model is valid. Also, it gives us the benefit of visualization of melting resulting crystallization of PCM inside the collector. Therefore, it helps us to figure out, let's look at the right figure, around 1 p.m., that material is fully melted. Therefore, we got to the temperature to get this material fully melted. And then once it's cooled down around like 7 p.m., you will see the sharp slope that the PCM start crystallizing, and that's the latent heat release of this material, which used as a basically backup source to increase the water temperature. Next slide. So the other research work that is going on in my lab is defining an innovative thermal analysis model. The CFD models and the DNS models, they are all very good source of, very viable source of numerical methods. However, they are time consuming. So the purpose of this work is trying to define a model which can gives us the better insight of thermal behavior in a very short period of time. The start point of this modeling was defining what are the different types of heat transfer that's happening inside of this collector. Basically, we are looking at fundamentals of the heat transfer and basically mechanical engineering concepts. So these three types of heat transfer, convective heat transfer, radiative and conductive heat transfer, in this type of collectors, they happen simultaneously. So when we are trying to model the collector, it gives us the CFD challenges as well as they are time consuming. That's why a modified resistant network model is developed for a collector. As you see on the right, the cross section of the collector is defined, and then we divided the collector into different arcs. So in each of those segments of the collector, all of these governing equations of the simultaneous heat transfer modeling are solved at the same time. The data is captured, and then our base point was basically we needed to define the operation of the collector into two different operations, the morning operation and the nighttime operation. So the morning operation time was solved by a model that we developed, which is resistant network POD model, a proper orthogonal decomposition method, and then for the nighttime operation, we developed the lattice-Boltzmann method. So therefore, the last input of the daytime operation, we used it at the initial input for the nighttime operation to give us the 24 hours operation that we are looking. On the left figure bottom, it shows a kind of a sample results of the temperature distribution for a collector. And then the good thing about it, this whole simulation that I just described, it only took 500 seconds to capture the whole temperature profile of the collector, which is basically very good result. Next slide. So I mentioned we are utilizing energy storage materials. However, we would like to make these energy storage materials in a way that they can absorb more amount of heat and they can transfer more amount of heat to our collector in order to have a better efficiency. So that's why we are using thermal analyzer devices, differential scanning calorimeter, and the thermogravimetric analyzer in our lab in order to predict and create a material with higher thermal properties. Next slide. So the DSC measures the difference in heat flow rate between a sample and inert reference as a function of time and temperature. So the reference sensor, it needs to be the same pan that we are using on a sample sensor. When we apply the sample on the sample sensor, when heat is absorbed by the sample, it gives an endothermic response. And when the heat released by the sample, it gives an exothermic response. In order to create that high thermally, high basically heat storage and heat transfer material, we again targeted back to our sugar alcohol sweetener, the cheap one. We integrated the nanoparticles in it with high thermal conductivity, as well as to increase the stability and have a uniform mixture. We are adding the dispersant 3-ethanolamine, so that would be a TEA to create our nanocomposite. Next slide. So we balance these materials in an electronic balance to make sure the weight matches for all the samples that we created. We heat them in the oven for 150 C, and the temperature is basically in a way that we know that all these PCMs are fully melted. We put the vials, we cap and seal the vials in the sonicator, and then heat it. Basically, that's a heated sonicator. Leave it there for 200 minutes to make sure these nanoparticles is uniformly dispersed in the mixture. And then we send the sample samples to the TGA to make sure there's no decomposition. If these types of material decompose at a certain temperature and you use them outside in your collector, it will just give you a leakage, and that's not something we wanted. That's why we need to make sure they don't decompose in the operating temperature. Once the TGA analysis is done, we send the sample to the DSC to see what are the thermophysical properties. So the figure on the right is just a sample of the preliminary result we got, and we see that in the mixture that we had the erythritol, sugar sweetener, and the CNT as a nanoparticles plus our dispersant, we could increase the specific heat capacity, which is the thermophysical property of a material, to transfer, or basically to enhance the heat transfer by 12.32%, which is a great achievement. So we are still working on it to get a better mixture with higher stability and higher thermal properties. Next slide. So currently UMKC opened a new plaster-free enterprise and research center. It includes a renewable energy lab and roof deck with direct access to the lab. It also has lots of other opportunities of the 3 million worth of new virtual reality, augmented reality equipment, a structural and construction materials laboratory, nanotechnology clean room, and makerspace for student computation teams, which is basically gives us lots of opportunity for the students. And it's open in August 2020. So you're welcome to stop by anytime you're in Kansas City, and we'll be happy to give you a tour. Next slide. So currently at the roof of renewable energy roof deck, we are installing the largest scale solar collectors. We started off with the smallest scale to make sure the proposed methodology is feasible, and that's why we are transferring to the largest scale setup. Next slide. And these are my graduate and undergraduate students working in the path to make the world sustainable. And next slide. Thank you for attention. I'll be happy for a Q&A and any upcoming questions.
Fantastic. Thank you so much. So many great things that you're working on. I am glad you're able to come today. So the next session, or the next speaker, is Michael from Electric Power Research Institute. Michael, take it away.
All right, Josh, can you hear me?
There we go. Yep, gotcha.
Excellent, appreciate it. My name is Michael McCrae. I am a regional executive for the Central U.S. region with the Electric Power Research Institute. For those of you who are not familiar, EPRI is a nonprofit organization, which is the research and development arm for the electric utility industry. I have several topics I'm going to cover in terms of EPRI's work, ranging from workforce development to decarbonization. And given that I have 15 minutes to move through all those topics, I'm going to go ahead and get right into it. The first initiative that I want to highlight is our Grid Ed project, and specifically the Great with Data initiative within that. This is an effort which is funded by the Department of Energy and EPRI members, which will prepare the future electric utility workforce for the intersection of the physical power systems and the digital systems that enable an integrated grid. It is focused on bringing together operational technology with information technology and creating regional training hubs through partnerships with universities. There are 5 areas of technical focus that you'll see on the left grid: power systems fundamentals, integration of distributed energy resources and end-use technologies, information and communications technologies, cybersecurity, and data sciences, including data analytics and artificial intelligence. The principle of Grid Ed and Great with Data is to create a pipeline of curriculum for all levels of experience to develop, train, and educate the next generation of electric power engineers. This includes reshaping university curriculum to develop new engineers, provide professional training for the existing industry workforce, and knowledge transfer from those retiring and leaving the industry to provide a total learning experience. There are 4 main objectives, which you'll see on the right-hand side. First is to advance workforce knowledge through a robust professional training program, which provides new skills and knowledge that are needed, as well as professional development hours for power engineers, and a key benefit for hiring and retaining utility employees. Second is to build strong relationships between electric utilities and local universities, which are the main source of new hires, as most students are likely to stay local. And the initiative also establishes exceptional professors, which is key to student interest and building a top-tier hiring pipeline. Third is to engage students to expand the electric utility talent pool of the next generation. This requires an interested body of students, which can be encouraged through undergraduate design, project sponsorships, and engaging students via conferences. Finally, is to leverage research by EPRI and other institutions in power systems and the smart grid at these partner universities. The methods for delivering this project include regularly scheduled live in-person and online professional training courses, a growing library of self-paced computer-based training through the EPRI-U platform, workshops with university professors and undergraduate design projects, and finally developing relationships with HR organizations within our partner utilities to advance workforce development through a learned experience. With these analytical tools in hand, power engineers and utilities will be better able to leverage technology such as artificial intelligence, which brings me to the next topic. Go to the next slide. AI.EPRI is an accelerator for leveraging artificial intelligence within electric utilities. We're bringing together utility and industry experts with data science platforms to address key industry challenges. This initiative is providing two components to address these challenges: expertise and data. EPRI's team of electric power industry experts are collaborating with the AI community to accelerate the application of AI to the right problems within the electric power industry. There's a lot of hype around AI, but this initiative is laser focused on solving big industry challenges utilizing AI. Curated data is key to solving these challenges. In machine learning, there is an 80-20 rule. Every data scientist spends 80% of their time on data pre-processing and 20% on their time of actually performing the analysis. EPRI is a trusted collaborator with the electric power companies where members provide us with data such that we have multiple industry-wide databases as seen on the slide. We can gather a year's worth of operating experience and data in a day. Our experts take that data, review it, label it, and prepare it for AI applications. Move on to the next slide. Here's a list of several of those applications. A few that I want to highlight that are applicable for today's discussion include T&D inspection imagery. As utilities are deploying more and more unmanned aerial vehicles, or UAVs, or otherwise known as drones with cameras, they're collecting terabytes of images of T&D components. EPRI is compiling and curating these images to provide AI vendors with the volume of images needed to train their platforms to identify components and to identify components that are in need of repair or replacement. On the customer side, AMI clustering has the potential to use circuit level data for understanding customer usage behaviors by identifying changes in those behaviors over time. This could allow utilities the ability to automate customer segmentation that adapts to changes in behaviors over time and provide faster identification of candidates for new products and services such as demand response. Similarly, HVAC fault detection is looking at the potential to use data from AMI to detect equipment degradation, potentially providing utilities with a new service to offer customers and providing customers with the ability to repair or replace equipment prior to failure. Let's go on to the next slide. AI.EPRI projects have also leveraged Incubate Energy, which is EPRI's network for bringing together startup companies with established electric utility companies. The Incubate Energy Labs are a collaborative demonstrations program, which links startup companies that are leading the advancement of electrification, decarbonization, and grid modernization with utilities from around the world that have the capacity and desire to demonstrate and scale those innovations. Within Missouri, Ameren has been a key supporter for the labs and hosted 4 demonstration projects in 2020. One example is a demonstration that was performed with INDT. Over the course of this demonstration, Ameren and INDT worked together to deploy 15 sets of early fault detection data collection units, one including a weather station, on sections of Ameren's transmission and distribution system remotely located near the state line of Illinois and Missouri. The team explored the ability of the early fault detection system to gauge timeliness of insights, prevent and mitigate potential issues on the grid, and measure avoided cost and ease of use by the utility's transmission and distribution team members. A second project with Recurve, in which a piece of Recurve software was applied to 200,000 AMI meters of Ameren's business customers to understand how a utility could use its AMI data to identify specific opportunities for energy efficiency and demand response for its customers, while optimizing cost effectiveness, streamlining customer acquisition, and delivering maximum benefit to the grid. This particular project focused on identifying specific solutions from Ameren's energy efficiency portfolio, which could be delivered to businesses hit hardest by the COVID-19 pandemic. A third project, which Ameren did not host, but relates back to workforce development, and Ameren is actually able to leverage as part of the collaborative project, is a demonstration with Cognitive Spark, which offers a remote support solution that uses the Microsoft HoloLens hardware to connect field workers with subject matter experts for real-time, secure, low bandwidth assistance wherever in the world they are located. This is an example of how augmented reality can be used to assist utility personnel on the job, enabling them to operate safer, more efficiently, and with increased productivity. We'll go on to the next slide. To further transform the grid edge, EPRI is hosting a portfolio of decarbonization demonstrations at community scale for customer resilience, energy affordability, and grid optimization. These demonstration projects bring together energy efficiency, local generation such as solar, energy storage, electric vehicles, and other electro technologies, building decarbonization, the Internet of Things, and customer engagements to optimize energy within communities. With these projects, the industry is focused on a few key research questions. What are the technologies needed to decarbonize and electrify existing buildings? Can we design these technologies to integrate hyper efficiency and grid flexibility? Can new business models for customers help to scale low carbon buildings and communities? What are the costs and benefits of using customer-owned DER to provide specific types of grid services? How can we transform underserved, low-income customers and small businesses using emerging technologies to create these smart communities? And how do we incorporate electrification impacts and load management into distribution operations and planning? Next slide. So as you can see, there are a number of these demonstrations taking place across the United States, including a zero net energy farm in Minnesota and a resilient university hospital campus in San Diego, as well as affordable housing retrofits and a smart thermostat evaluation, which Evergy participated in a few years ago. Next slide. One of the key components of these smart communities is electrification. Electrification provides many benefits to utilities, including, I think we need to go back, there we go. And electrification provides many benefits for utilities, including mitigation of decreased load, as well as demand response for grid flexibility, but also provides value to utility customers through energy efficiency, decarbonization, lower cost, and improved air quality and safety. At EPRI, we'll look at electro technologies broadly in three categories. First is mobility, not just electric vehicles, but also looking at aviation, shipping, shipyards, warehouses, forklifts, etc. The second category is heating and cooling. This can be for residential customers, as well as industrial facilities and power plants. Additionally, that we are looking at the use of radio frequency for drying of grains, biomass, and other agricultural products, and applications in food processing, textile, and other areas, in other industries. The final category is new applications. These are new technologies such as indoor agriculture, 3D printing, and other emerging technologies. But electrification is not always the answer, as parts of the economy are very difficult to be able to electrify. So EPRI has partnered with the Gas Technology Institute on the Low Carbon Resources Initiative, or LCRI. So we'll go on to the next slide. LCRI is a 5-year initiative to advance low carbon energy carriers like hydrogen or ammonia. Through a better understanding of the production, transportation, storage, and end use of alternate energy carriers, the LCRI can support the energy industry in multiple areas. It supports the integration of renewables through the storage and use of alternate energy carriers for generation and grid support, provides a better understanding of the potential opportunities and risks that are associated with transportation of alternate energy carriers through the existing gas infrastructure and any impacts upon a utility's gas business. We'll look at the utilization of existing generation assets for production of alternate energy carriers, and it looks at enabling an indirect electrification to provide support for existing investments in generation and transmission assets and grid modernization. Also determines the applicable use of alternate energy carriers for transportation, heating, and other applications to help utility customers and communities in meeting their carbon commitments. Understanding how all of these goals can be achieved, and finally, we're looking at understanding how all of these goals can be achieved in a safe and affordable manner. Specific to the central U.S., one of the key means of production of alternate energy carriers is through electrolysis, leveraging low carbon generation resources. With a large potential for wind and solar generation in the central region of the U.S., Midwestern states could play a major role in an energy system based on hydrogen and other alternate energy carriers. Additional information about this project can be found at lowcarbonlcri.com. With that, I'll go ahead and turn it back over to you, Josh.
Thank you, Michael, so much. Our last presenter today is Jennifer from the National Renewable Energy Laboratory.
Hi, thanks, Josh. Just to confirm, can you hear me?
Yes.
All right, terrific. Well, thank you so much for the invitation to come and speak with you today. This is a great panel to be part of, and I'm just really excited to be here. So I'm going to give you an overview of a relatively new program at NREL, which is our Advanced Research on Integrated Energy Systems, or ARES. And to give you a quick introduction on myself, I'm the director of NREL's Energy Conversion and Storage Systems Center. And I have the great opportunity to work with a very talented team, cross-functional team. And so I just like to acknowledge their contributions to this program, as well as our very critical partners at the Department of Energy. If you go to the next slide, please. I want to give you that overview. So I'm going to tell you a little bit about ARES. And on our next slide, this is the mission, if you will, of ARES. And so what we have seen is new opportunities come up with our energy system. Renewable generation costs have come down. We have more and more deployments, and we recognize that our energy system is changing. It's quickly changing, in fact, and the complexity and the different configurations that we see as possibilities are growing as well. And so what we are looking at is a research platform that can match that complexity of both the near-term energy system, but also the longer-term energy system, and look at integrated research to support the development of groundbreaking new energy technologies. On this particular slide, we've identified 3 fundamental challenges that we're working on. The first is variability in physical size. When we look at these new energy system configurations and possibilities, we can have technologies that are quite small and all the way up into the bulk grid. The second challenge, fundamental challenge that we're working on, is securely controlling large numbers of interconnected devices. And I think we see this in our day-to-day lives, where we have more and more things that we can talk to and plug in and control. And that's actually been discussed already on this panel. And then the third fundamental challenge is integrating all of these diverse technologies, especially when they haven't been integrated in the past. And so again, these are the 3 fundamental challenges, and ARES is this research platform where we can de-risk, optimize, and secure both those current energy systems, but also those future energy systems. Next slide, please. So I've laid out the fundamental challenges, and the next piece, I want to show you how are we going to go about looking for innovations and solutions for those challenges. The first is we're looking at 5 research areas that are identified on this slide: energy storage, power electronics, hybrid systems, future energy infrastructure, and cybersecurity. Each one of these research areas has a diverse set of research challenges and strategic objectives that we're going to be going after, but also these are all integrated together. And so when we look at energy storage, we also want to look at the cybersecurity of those technologies, or the power electronics, or how they fit into the whole system. So this is the kind of the research focus. And the next slide, I'd like to tell you about the research platform. This is our integrated research platform, a high-level summary of it. On the right-hand side of this slide, we're looking at loads and storage primarily. And we have a facility called our Energy Systems Integration Facility, where we have been looking at these different grid edge devices, if you will, batteries and building loads and things like that, all kind of under this 2 megawatt scale. When you go to the left-hand side of this slide, you're looking at our integrated energy systems at scale, which is at our Flatirons campus. And this is where we move into the generation and storage and that transmission and distribution hardware capabilities up to about 20 megawatts. And so these are 2 different hardware capabilities that allow us to play in that sandbox of different system configurations. Now, an important piece is shown in the blue cloud in the center top of this slide, and that's a virtual emulation environment. And I think Casey had talked about this a little bit too. We're looking at this as our ability to play and expand the types of configurations, increasing the number of devices that are connected within our energy system. And we aren't able to do that with hardware. So we're coupling a virtual emulation or a ability to mimic or replicate some of these technologies or systems, also combined with this hardware capability up to about 20 megawatts. So this is the 3 legs of our research platform. Now, if we go to the next slide, please, I want to highlight just a couple of things that are going on right now. This is a snapshot of one of our laboratories at the Energy Systems Integration Facility, or ESIF. And this is a smaller system. You'll see that we have on the left-hand side of this image, we have vehicles and charging stations. On the right-hand side of this image, we have laboratory setups that help us mimic and replicate commercial building loads as well as residential building loads. What we're doing in this laboratory is setting up that integrated system so that we can look at the controls, we can look at the optimization, we can look at the communication aspects, all pulling in our modeling with this hardware capability so that we can have validated results that put together, in this case, looking at, let's say, a commercial building with extreme fast charge or fast charge capabilities, and how can you control that whole system together. So this is just one example of an active research project looking at that integration and pulling together multiple sectors of our energy system. On the next slide, we have a snapshot of the Flatirons campus that I talked about. And so this goes up to the 20 megawatt scale. And another thing that I just want to reiterate that's so important is our ability to integrate and to have representative scaled systems. So we're really studying the science of scaling. And we're talking about putting multiple technologies together. I really didn't touch on it, but we've got a lot of different energy storage technologies. Michael was just talking about hydrogen, for instance. We have hydrogen on this campus. We've got battery storage. We've got multiple generation technologies. And then we also have an ability to control the operating conditions for these systems. And this is really exciting for our research staff and our partners, because not only can we look at both the ideal configurations and operating conditions, we can go beyond that and we can look at out of bounds operating conditions for these systems so that we can help find those consequences before these systems get deployed into the real world. Now, if we go to our next slide, this has really been something that I found interesting with the talk so far today and ideas. We are very interested in recognize that there are many different expertise and capabilities that are across the US and internationally. what we're showing on this particular slide are some key connection points, key partnerships that we've already identified that will be really important for having a wide range of energy systems that we are integrating and studying. So a couple of things that I want to point out on this particular slide. One is looking at other national labs. And we have a great ability to connect with laboratories, let's say on the Northwest with Pacific Northwest National Lab, and they have a grid storage launch pad and additional expertise with some of the energy storage technologies, in particular batteries. And how do we connect with that? And how do we look at the full range of research development, right? From early stage research into this applied research and the systems integration and moving it into the marketplace and technology. Another thing that I'd like to point out is our interest and connection with both industry and academia is going to be so important. We've heard about some of the student activities that are going on right now that are led by our professors and talking about workforce development. We think that this is going to be a really important research platform to make some of those connections and really expand the capabilities of not only our students, but also our workforce. So I think that that's a really exciting opportunity, in my opinion, for us to be looking at and building off of. So I just have two more things that I'd like to wrap up with. And the next slide is looking at what we call our differentiating characteristics. Now, there are a lot of people with tremendous capabilities and expertise in different aspects of our energy system. What we see and think that ARES is very important for is that the energy system complexity is rapidly increasing, and those traditional system boundaries are changing. And so what we want to do is pull together this research platform, the capabilities and the modeling and the hardware, so that we can look at infrastructure at scale. And again, you know, we're looking at everything from benchtop up to 20 megawatts for hardware systems and then beyond with that virtual emulation capability. We also recognize that flexibility is going to be so important. Those system configurations are going to be changing as new technologies are developed, as we find out new things when we put these technologies together. And so with our research platform, that flexibility is going to be so important so that we can look at different configurations, we can look at different operating conditions and really study and characterize and innovate. Another characteristic that we think is really important with ARES, that's this system view. And so we have deep dives going on in different energy technology spaces. But until we put those things all together, there's still unknowns, right? That we still don't know how these things are going to operate. We aren't quite sure what we're going to see for actual performance, and we need to quantify what we think the benefits are. And that's that connection with modeling, analysis, and experimentation. And then the fourth thing that is so important here, pardon me. The fourth thing that's so important is partnerships. Now, we want to make sure that the research that we're doing under the ARES program is impactful. And one of the ways to measure impact is to look at innovations that are getting implemented into the marketplace. We want to accelerate that. So having partners, industry, academic, national labs, right? Those partnerships are so important to us being successful. And we're setting this up so that we can have those partnerships, whether it be with people on site or virtually connecting with data, connecting with other technologies and other experts. So for my last slide, I just wanted to hit on what's next. So what are we doing? We've got parallel paths going on right now. And one is we've got a lot of research already active in this advanced research on integrated energy systems, or ARES. We have research in all 5 of those research areas. And in parallel to that, we're actively building out capabilities. And those capabilities may be with specific technologies, but it may also be with integrating those technologies together, working on the connectivity, working on the cybersecurity aspects and the communication aspects of those. So that's all active right now. We have plans, multi-year plans for those capability build out. And then one example of some capability that we're looking at right now is 100% renewable microgrid research platform. And this is really exciting for us because we can look at that integration research, we can look at the optimization research, but also the monitoring and protection schemes and scenarios of interest, especially with future energy systems. So I thank you for your time and I hope this has been informative. We do have more information on our webpage if you go to nrel.gov and get more information there. And certainly I'm always open for questions. So thank you.
Thank you very much, Jennifer. Michael, Casey, Sarvanaz, if you want to hop back on, fantastic. So there are a couple of questions. The first one was directed towards Casey, and there was a question from Eric Hempel. Are there any benchmarks for permitting time from your study?
Yeah, so I mean, in terms of benchmarks for the SolSmart program, at the gold designation level, they're trying to get communities to a 3-day turnaround for permitting. Before that, I would say that it's really a matter of going from like weeks to days. So in our study, we found that SolSmart communities had faster permitting times, and they were faster by about a week.
Okay, great, thank you. Sarvanaz, Donnie Clark asked if you could talk about the comparison between your product and a heat pump water heater.
Sure. So first of all, thanks for the question. That's a very interesting question. So heat pump water heaters and basically the solar water heaters, they are actually in one box. That box is compared with the conventional water heaters where they use electricity, gas. So in the box of heat pump water heaters and the solar ones, they are less, basically they are more environmentally friendly. So there will be less pollution out of those, as well as what we are saying is just to have a green board and sustainable, that will just help us to pick the solar water heaters. But other than that, the price, the cost of those two are less compared with the conventional water heaters. However, if we would like to compare the heat pump with the solar ones, the analysis up to now, they are for solar boosted units, which they still require a booster system which works with electricity. So at this point, for my proposed technology, we didn't do the economic analysis of the system to figure out removing of that booster unit, how it affects the total cost. Other than that, the solar water heaters, they are there's basically one deficiency of those, which is the space. They require the space that you will need for the installation of those collectors. Again, with the technology that I propose, the type of the collector that we are targeting because of the high efficiency with a smaller space, therefore it also kind of minimize the amount of required space needed for installation of the solar panels. So that would be a very great future work for us to do the solar energy storage water heaters compared with the heat pump. And that would be a next, PhD students or master's students to go for that project. Josh, I think you are muted. Josh, you're muted.
I did it myself. So a question for all of you is understanding the utility customer is really important, not only for the utility, but also for the research that's being put in play. Can you talk about how each of you are integrating in the differing utility customers as well as the utilities in your area or certain utilities with your work? And we can start with Jennifer and then Michael, Sarvanaz, and then Casey.
Yeah, certainly. Utility partners, we have, we consider them very strategic partnerships for the research that we're doing, especially with ARES. And so we have a number of active research collaborations. And then also with our own local utility, not only do we have active research collaborations, but For instance, I was just talking about that 100% renewable microgrid, and that was actually triggered and kickstarted by a substation failure that we had on our campus that was separate from any research activity. But we worked very closely with our utility provider to set that up and not only study and look at what the operations are, but also that monitoring and protection of the system. So we consider them, again, very strategic partners and much needed for us to actually move research into the marketplace.
And before we go on, Michael, I guess, let me clarify there, Jennifer. The question was really around the utility customer. I know I asked about the utility as well, but
Oh, okay.
do you look, so no, I thought what your answer was good in general. And if the others can talk about the utility as well, but the question that was provided to us was the utility customer, and I would, the different sectors. How do you deal with that and thinking about the work that you're doing applying to them?
Okay, my apologies. Thanks for the clarification, Josh. When we look at the loads, and that's where I'll put kind of the utility customer side, that there's a wide range of loads and different scales. So it fits nicely with the 3 fundamental challenges that we're trying to address with ARES. What we're looking at and kind of changing our thought is that generation to load is no longer a linear path, right? There's bi-directional activities happening. And that's where I think we've got a lot of opportunity around the integration and understanding the utility customers and their loads, what they expect, what their requirements are, and what those demands are.
Michael?
Yeah, so I think a couple of things in regards to that question. First off, EPRI has an entire research program that's dedicated to understanding the utility customer and works very directly with a lot of our other programs in terms of understanding, customer adoption for certain different types of technologies, rate structures to encourage those types of technologies, like charging infrastructure, those types of activities on the consumer side. And that's going to be, I think, the key piece across all of these is, as we move to some of these new technologies, customer adoption is really the key aspect behind that. It doesn't do us a lot of good in terms of being able to develop these technologies if there's not a benefit for the customer, value to the customer, being able to adopt those, implement those into regulatory structures, those types of activities. And I think that's an area where EPRI can really assist with some of the university research and providing some of that feedback and some of that type of perspective as universities are looking at all these different technologies and being able to leverage some of EPRI's understanding really when it comes specifically to utility customers, the segmentations around those customers in particular. There's obviously major differences between residential, small commercials, and large commercial industrial types of customers, their needs and what they're looking for. So that's a perspective that I think EPRI can add into the university side.
Great. Sarvanas?
Sure. So utility customer, well, first of all, I also started my talk targeting the customer and the demand side. So the project that we are working on at this point is just purpose for residential customers. And that's why initially, before doing any modification to our systems, we need to make this infrastructure ready to just basically motivate the customers to purchase our technology in a few upcoming years. So we started looking at the load that Jennifer mentioned. So we need to make sure like the different household with different number of people and the square feet that they have. What are the limitations of each household? We take a look at those, as I mentioned, the space requirement, as well as other stuff. And then the budget is so important for us. The cost analysis is very important for us to make sure whatever technology we are developing and we are just improving or working on it, it's still budget friendly. So we at this point cannot 100% compete with the electricity price or basically the gas price specifically. However, we are targeting to make it in a way that the customer will be most interested to just pay this upfront cost. So the upfront cost of the solar water heater technology is a little bit expensive compared to the other costs. However, we are trying to make sure that the life cycle of this device and the payback money of that will be still interesting for the customer utility part.
Great. Casey?
Yeah, so I really appreciate this question because a lot of my research is kind of at the intersection between behavioral science and engineering. And so from my perspective, you know, I love having partnerships with people. And so I think it's really important to build these partnerships and make sure that, you know, the utility voice is heard, the utility customer voice is heard. And in my mind, one of the best ways to make sure that, you know, we're incorporating the perspective of utility customers is by doing, for example, human subjects experiments where we actually go and ask people and do surveys, do interviews to actually capture those perspectives. And so, you know, after coming up with some kind of technical solution, actually going to the next step and doing the behavioral research to figure out, okay, from a technical perspective, this works, but if we actually implement this, does it also work from a behavioral perspective? So yeah, I completely agree. It's really important to consider that perspective.
Great. There was one last question here from Tim Michaels. Jennifer, that was, how involved is NREL in community energy systems that focus on integrated approach to optimizing efficiency of existing communities, especially with respect to economic and environmental justice issues, with local site wastes conversion to power and heat and renewables, all predicated on their actual local economic development, an LCOE.
All right. So Josh, I'm not sure that I'm going to remember all of those to hit on, but and I realize too that we have to be careful when I talk about ARES and this integrated research platform. We realize this isn't solving everything, and we still have a lot to achieve here. But with the communities in particular, what we see as a really exciting opportunity, I flashed that snapshot of the fast charging with kind of building simulations and that hardware piece. One clear connection that we have is to expand that from one building to a community. And there's opportunities out on connected communities, for instance, right now, that this is a real important focus area. And that scaling, that variability in size is such a key aspect of what we're trying to do with ARES. One other piece that I thought was really important in that question and connection to ARES is the affordability, right? Just because we have a great looking system that we put together either in a model or with a set of hardware in a laboratory experiment or even our real world kind of larger scale system, if that isn't affordable, if it isn't achievable and able to move into the marketplace, we still haven't achieved what we set out to do from a research perspective. So it's not just a clean system, it's not just a sustainable or flexible or resilient system, it is an affordable system too that is so important, and at scales that go down from individual households up to distributed systems, bulk systems, and that community resides inside of that. Great.
Well, are there any, that actually wraps up all the questions that we have. I can say personally, I'm really glad that the 4 of you are out there because there's no way I could figure any of this stuff out. So I greatly appreciate all your work personally. It's really exciting to know what's going on there. To me, what I find most interesting are in every single one of your projects, you are collaborating with a variety of different entities, and I think that really demonstrates a greater likelihood of success afterwards. So that brings me a lot of hope for that. So thank you all very much for participating today.
Thanks, Josh. This was great. It's a lot of fun.
Appreciate it, Josh.
Absolutely.
Appreciate it. It was very good.
Our